All right, we're now going to have a look at the states of matter, so the solid, the liquid, and the gas, and we're going to focus on qualitatively describing what's going on macroscopically and microscopically, and relate sort of what's happening to the individual particles to what we can observe macroscopically. So our objective is to explain the physical differences between solids, liquids, and gases in terms of molecular structure and particle motion. And we're going to do this by having a look at a simulation which allows us to look and compare what's going on with macroscopic sample and relate it to what's going on with the individual particles within that sample. And we'll do this by looking at a small sample of neon in its solid state. It's at 13 Kelvin at the moment, which is very cold. And at that temperature, neon is in its solid state. And so what we can say, first of all, is that macroscopically this sample of neon appears to have a fixed shape and a fixed volume. The density is high. Alright, so these are the three things we're going to have a look at, and we're going to now take a closer look at the microscopic reasons behind these observations. So firstly, we can see, if we're looking now at the particles, we can see that they're very tightly packed. And the reason for this is that they're held together by very strong intermolecular forces. And the particles also, we can see here, have vibrational kinetic energy. They're not standing still, they do have kinetic energy. And in fact, we can increase this vibrational kinetic energy by adding a bit of heat. You can see that the particles begin to vibrate more. And if we remove heat, the particles vibrate less and less and less. And so the kinetic energy in the solid is all vibrational, and the particles, what I mean by that is that they do not rotate and they do not translate. They don't translate through the solid, so this particle will always remain in the same position within the solid. That'll probably make more sense once we've started looking at liquids. And so the particles do have kinetic energy, they also have potential energy. And the potential energy is due to the forces of attraction between the individual particles. And again, we're going to explain clearly what we mean by potential and potential energy when we come to topic 6. So for now, it's enough to say that they have both some kinetic energy due to vibration and some potential energy due to their the forces between them and their position relative to each other. Okay, we'll now have a look at the liquid state, and I've changed this now to the liquid state in this simulation. And from experience, we know that a liquid has a fixed volume, but it doesn't have a fixed shape anymore. So if we pour a bit of liquid water into a container, it will change its shape to match that of the container. The density of a liquid is still very high, and all of these things are represented here in the simulation. We can see that we have a kind of fixed volume blob here of liquid, and we can also see that the blob is kind of changing shape, and we can tell that the particles are still very tightly packed in together. Okay, so to explain this microscopically, we can say that the particles are still tightly packed. They're held together by intermolecular forces still, but it looks like the forces have become much weaker. The particles are now free to slide past one another and to move around within the within the sample of substance that we have, so within the liquid. And so the forces that are holding the particles together are no longer nearly as strong as they were in the solid state. The particles themselves still have some vibrational kinetic energy, but they also now have some translational kinetic energy. In other words, they can move around. They're not just vibrating. And they also have rotational kinetic energy. They can spin or twist now, which they couldn't do before. And in this state, in the liquid state, the particles have much more potential energy. And so by breaking those strong bonds that we had in the solid state, we give the particles much more potential energy. Okay, we'll now take a look at the gas state. And we know from experience that if we put a gas into a container, the gas will expand to fill the whole container that we've put it into. And it will also adjust its shape to fill the container that we've put it into. So macroscopically, a gas has neither fixed shape nor fixed volume. The density of the gas we know also is much lower than the density of a liquid or a solid. So if we have the same amount or mass of a substance in its three different states, the gas state will occupy much more volume. If we look microscopically at what's going on, then we can see that the particles are no longer tightly packed as they were in the solid and the liquid. In fact, they're much further apart than they were. The forces between the particles are the attractive force that was holding them together in the liquid and the solid. They appear to be much weaker, and that's because the particles are now much further apart. The individual particles no longer exert as much force because the particles' average separation is much bigger. There is one time when they do exert a force on each other, and that's during collisions. Okay, the particles, they'll move around randomly, and they collide with each other and with the walls of the container that they're in. And the kinetic energy of the particles appears to be largely translational, so the particles are moving around within the container randomly. But if we have a look at water molecules in a gas state, we can see that they also have a significant amount of rotational kinetic energy. So in the gas state, there's both translational and rotational kinetic energy, and there's also vibrational kinetic energy in the particles. The last point to make is that the potential energy in the gas state is much higher than in the liquid or solid states. And that's due to the fact that the particles have been moved much further apart than they were when they were in the liquid, which means that we had to do work on the particles to pull them apart, because there was that attractive intermolecular force that was holding the particles together when they were in the liquid state. And so in the gas state, the potential energy of the particles is much higher. And so now we've had a look at the three different states of matter that we're going to consider. There are many other states of matter, by the way, but these are the three most common states of matter. And so they're the ones that we are focusing on. Next thing we're going to do is have a look at what's actually going on when we change states from a solid to a liquid, or from a liquid to a gas, and back again. And I've tried to emphasize the point that it has to do with the potential energy. So during the changes of state, as we change from a solid to a liquid, we're increasing the potential energy. And as we change from a liquid to a gas, again, the potential energy increases dramatically. So that's our next task.